These are all just good.
Yeah.
Were you able to step aside for 1 second?
Oh, sorry. Did we kill something?
Yeah. The tech support guy's right here.
Okay.
It's working there.
Yeah. If you just tear it into new pieces.
There's nothing going on.
Yeah.
Maybe. Oh, there's a red. There's a red. I have unplugged everything. Maybe there was too much. So like I said, I don't know. I get one, and I've had another one the other side.
Oh, perfect. Excellent. Just needed to be.
Good.
Cool.
Oh no, we're starting in half an hour. Yeah. Do It looks like the HDMI to Thunderbolts went missing. Like it's not up there. Do you have an extra?
It's in the other room.
Okay, no worries. Thank you. You've been so helpful. I'm so sorry to.
I'll tell you what's possible and what's not.
It's good.
Oh yeah. Yeah, yeah. Yeah, right. Yeah. Yeah.
Actually, there's one seat there. Huh?
All right.
It's okay, I'll find. Can you see that?
All right, I'd like to announce our next speaker, Sanjay Krishnan, who's an assistant professor at the University of Chicago, and his research focuses on applications of machine learning and control theory to computer systems that are able to adapt to changes in data, systems, and user behavior.
Cool. So thank you guys all for having me here. Today I'm going to talk about some of my research, and this is in collaboration with the UC Berkeley RISE Lab, where I did my dissertation work, and the University of Chicago, our new group over there. So the title of this talk is Learning to Optimize SQL Joins with Deep Reinforcement Learning. In essence, we're trying to look at what applications of deep reinforcement learning have this query optimization at query computation level. So to sort of really set the stage of this problem, here's database 101. SQL is a declarative language. So that means, suppose I have a data set of employees, salaries, and tax IDs. And I have this in 3 different tables, right? And I want to calculate some sort of quantity that requires integrating information across these 3 different tables. Like calculate the total tax owed. So that means I need to look up the employees, I need to look up what position they are, how much the salary for that position is, and then what the tax codes for each one of the countries are, right? So I can write this as SQL. Now the problem is that this particular SQL statement tells you what you want. It doesn't necessarily tell you how you can get it. For example, I could scan the employees table first, then look up the salaries, and then look up the taxes. I could build a lookup table on the Cartesian product of taxes and salaries, and then scan the employees table. I could sort one of the tables and then try to merge it in. There are all these different options that come up from this one SQL query. So the problem of query optimization is really taking one of these SQL queries and then figuring out one of these execution paths. Which one of these execution paths is the best? Okay, so the way that this happens today is that we take a query that looks like this, we come up with some algebraic representation of the constituent logical operations, right? That we want to merge employee salaries in the table and then taxes, or we want to do the other way around. And the key idea in query optimization is to define a set of algebraically equivalent expressions. Then a database system comes up with a cost model that tries to heuristically score each one of these expressions. Like the first one has cost 1,200, the second one has cost 120, and then it's going to pick this thing. Now, there are many problems with this world today, right? First, there is an enormous space of possibly equivalent algebraic expressions, and second, these cost models tend to look something like this. And this is obviously like facetious, but you know, if you dig up the Postgres source code or you dig up another query optimizer source code, it's going to look something like this. There are all these magic numbers, 0.1, 10, 0.3. These are just designed by some grad student or the developer at the time who thought this was a reasonable way of approaching this problem. So let's now think about how do query optimizers today actually work. So let's assume that this cost model was perfect. I tuned this by hand and I got this just the right way and it's going to work on all systems, right? How could we use this cost model to search through the space of possible bids? So let's look at the abstract expression join ES&D, employee salaries and taxes. Well, this turns into a dynamic program, okay? So we first figure out the best way to access each single table, which is itself a query. Then we figure out how to access each pairs of tables, the best way to access each pair. Then we figure out how to access the triple, okay? Now, as we can immediately see just drawing this out, even with a dynamic programming approach, the search space explodes. Now, if I had a 15-way join or a 20-way join as is common in visualization tools today, this is going to be an amazingly large search space. Okay, so what we have in most query optimizers, in addition to this heuristic cost model, is a tightly coupled heuristic search process. We have about 40 years of heuristics on how to prune this space. For example, most classical query optimizers will not go down that path, employees and taxes. ENT will just not go down that path, okay? And these heuristics often implicitly assume assumptions about the way that our databases are designed and the way that our cost models are likely to behave, right? For example, there's a classic heuristic called left deep search. It means we only look over orders that are left deep. We nest on only one side of these orders. Now that assumption roots into the fact that many databases have indexes, and usually indexes are on the left side of the join, and your probes are on the right side of the join, right? So there are these hidden assumptions that are baked into the very heuristics that we're using to service this problem. The other problem that we have is query optimization today has this one and done property. We optimize one query, we do all this effort to build out this dynamic programming table. The second a slightly related query comes in, like employees, salaries, taxes, and then something that starts with you, or employees, salaries, taxes, and maybe gifts or something, right? We have a clean slate and we start this optimization problem again. Again, because of the combinatorial nature of this problem, very hard to figure out what intermediate state to cache if we were trying to do this deterministic. And finally, the obvious third issue here is there's no feedback. This cost model can be arbitrarily different from the real world, right? We have a new cluster, we have new hardware, we have new other processes that are running on our server. Suddenly that cost model, which is a proxy for runtime, may start behaving very differently than what the actual runtimes are when you execute these queries. So we have these three issues. We have lots of heuristics, we have no shared information between instances, and we have no method for feedback, right? And the premise of this talk, in some sense, the punchline of this talk is DeepRL gives us a rigorous modeling framework to figure out how to address each one of these three problems. It is a formal way to think about all three of these problems by parameterizing the planning problem with something like a neural network. So let's talk about how we do that. So why is this problem a DeepRL problem, and why is it kind of Markovian in a sense, okay? So let's think about this in the abstract. So we have this query that is calculating the tax across these two tables, employees and salaries, okay? So we can think of this as a graph of employees, salaries, and taxes, and there are edges between the predicate relationships between these edges. I realize I have an extra and at it, don't sort of shoot me for that one, okay? So the way that join optimization goes is you start off with this graph, and you can think about this as figuring out how to incrementally reduce this graph in size, picking two vertices. So picking two vertices to join and creating a new graph. So for example, I have employees, salaries, and taxes. I have this graph. I can pick two of these vertices, say employees and salaries, join them, and now I get a new graph. Okay? So I incrementally make this graph smaller until I get a singleton, or the number of connected components in this graph in general. So now this process is called a graph contraction, but we realize that it's isomorphic. Enumerating all the possible graph contractions is isomorphic to enumerating all the possible joins. We have this query graph, we have these contractions, and then we have a final result at the end. And this process defines a join order, employees joined with salaries, joined with taxes, okay? Now, so the idea, the optimization problem that underpins join optimization is we have this graph contraction where each one of these contractions has an associated cost. It has some expense to running that particular sequence of operations. So the problem is to find the minimum cost sequence of such contractions. But what's really interesting to us is this mirrors problems that we see in DeepRL. This is exactly a Markov decision process. The reason that I presented it in this kind of esoteric way is that the query graph in some sense summarizes the full state of the optimization problem. We don't need to know what sequence of joins got us to this intermediate state. We just need to know how to behave in the future, right? So we have a Markov decision process where the states are the query graphs, the actions are all possible contractions you can make. The reward is the join cost, the cost of the contraction, right? The analog to the cost model that we see. And a policy is to figure out, given a graph, select the next best contraction. So what this really turns into, the way to really think about this, is it's taking this dynamic programming table that we used to enumerate combinatorially before. So we have this combinatorial graph of all these different all the different states in our dynamic program and the associated costs. When we think about this in a DeepRL way, we're essentially saying, let's take this dynamic programming table and turn it into a parameterized model. The same way that a policy is a representation of a query graph and the next best join, can we take this dynamic programming table and represent this as a parameterized model? In essence, taking this thing and compressing it down with the capacity of a neural network. What this really allows us to do is start to think about all of these problems as AI problems. Classically, in query optimization, we think about feedback as this complex process where we have to update histograms, update table statistics. Maybe feedback can just be thought of as fine-tuning a model. We train a model on a cost model offline. We train this. We collect all these observations of different joins on a cost model. We train a deep network that represent the dynamic programming table, and then we update it online with query feedback. But the cool part is, the second that we train this model, which is actually just a queue function, right? Taking the current join and the next best join to make, it actually allows us to speed up planning as well. By taking this table and turning this into this queue function representation, an equivalent definition of a queue function is it is a cost function over which greedy descent is optimal, right? So once we've learned this functional representation of all the possible tables and all the possible intermediate states and the next best join, which is obviously an approximation of the real world, we can just simply greedily descend down this function to get a plan of what our model says. Now, the really cool part about this is that when we put this into real systems, we see really amazing performance, right? We took out the PostgreSQL query optimizer and we replaced it with a learned model. So we did this on a workload from IMDb, and we collected a bunch of data. So we trained on 100 queries. We tested on, say, about 20 or 30 queries. And we see that for those tested queries, we can speed up planning time by up to 32x. And now, this is really significant because think about it, PostgreSQL is something that we've been developing as a community for 40 years, right? And now, to show any leverage on this problem is kind of amazing. And interestingly enough, even trained just on the data coming from PostgreSQL, we can actually speed up execution times as well with no feedback. And I'll talk about what happens with feedback, but it's kind of interesting that there are sometimes bugs in the cost model, and optimizing a faulty cost model is in some sense a form of overfitting. And when you use a neural network to represent this planning problem, in some sense, you can hedge for some of this overfitting, you can smooth out some of the issues. Now in systems with non-traditional cost models, like Apache Spark that are distributed, and there are all sorts of other physical effects like issues of network communication and so on, we can start getting amazing improvements as well. Now it turns out getting this right is really hard. I presented sort of the simplified story about like how we can take these SQL queries and turn them into these kind of nice parameterized planning problems and so on. But actually getting this right is really hard. Just because featureization is really tricky, you're in some sense featureizing programs here. You have the SQL query, and you need to be able to turn that into a set of feature vectors. And one of our key challenges is to avoid featureizing data. We don't want to get into the world of featureizing literals in our database. That just is sort of saying that we have a universal representation of all tokens that we can possibly see. We want something that is purely dependent on the schema, purely dependent on the structure of the query. So just sort of summarize how we actually turn this into a featureized problem. We have to featureize these queries and featureize that intermediate query graph. So this breaks down into what data is touched, so what tables show up in the query, attributes on the left side of the join, attributes on the right side of the join, and something about the type of operator that you're using, whether you're doing an equality join, whether you're doing an inequality join, greater than or less than, or some sort of a theta join. So it doesn't work for arbitrary expressions, right? It doesn't work if I have a user-defined function. It doesn't work if I have something complex in there. We really need to know, and I think that this is one of the hard problems that we've seen that we really need to focus on as a community going forward, is how do we really featureize queries and tables? It's kind of a really interesting representation problem, and something that the machine learning community should kind of embrace, because these are nice combinatorial hierarchical structures. Perhaps there's some elegant ways to think about featureization and representation. So all of this tends to be one hot encoded. This is a completely binary featureization, and as we said, that there are all sorts of other things we can do. Now, we also do some additional stuff, like we propagate information from the underlying table statistics when we have filters and additional types of artifacts inside the query. For example, if I have a join query that is joining employees' salaries and taxes, and I have an additional filter that I only care about employees and salaries and taxes for a particular set of employees, I can add this as an additional filter, and we propagate that information into feature representation, like what fraction of those records are taken. And this is done deterministically from underlying estimates inside the database. Now, one of the cool parts about this is, so I showed you the end-to-end results, but where does this really win? This really wins when we run this on cases where we have non-traditional database designs. So existing heuristics work really well when the database is designed in a way that is kind of matches the assumptions of the heuristics, right? So when we have a database that is well indexed and is kind of looking at an index mostly query plan, that means query plans that prioritize these indexes, the classic left deep strategy works really well. There's no reason to do anything other than that. But the second that we start working in models that are non-traditional, either a distributed database or one that persists as hash tables, we start seeing that the learned query optimizer behaves much more efficiently and much more accurately than the options that we have today. Now, the other option that we find is really exciting is we can start also collecting data online, because these are parameterized models. We can fine tune them from real execution, right? And we find that we not only match the performance of existing optimizers, not just optimizing planning time, but we can significantly improve execution time, because we can feed that information back easily to a parameterized model. So we tried to exhaustively canvass the space of all the different heuristics that are used today, and we find exactly this across many different cost models. So one simulating something that's going to be in a row store, one simulating something that's going to be in a columnar database, one simulating something that's going to be in a parallel database. We find that our system is robust to the cost model. It is sort of agnostic to the way that you're designing the cost model. In some sense, deep RL decouples the notion of reward from the notion of search. It is independent of the search strategy, sort of independent of the way that you're defining your reward, and it's learning to prioritize that search strategy towards a specific reward function that you're designing. So this is sort of summarizes the main gist of the talk. Why I, as a systems person, am excited about deep RL. There are a lot of problems in databases and scheduling, resource allocation, and so on, that we have an abstract objective, and we need to synthesize a plan or solution towards that objective. Now, what deep RL gives us is a framework to handle all of these three things, right? We in systems have classically sat down and wrote grad student-based gradient descent, right? We figure out heuristics to prioritize our search space. We have generally not had problems that share information across all of these heuristic planning and scheduling instances. And we have also had a hard time adapting to dynamic environments. Deep RL gives us a way of thinking about this problem. It gives us a disciplined framework for reasoning about and dealing with this problem. So just a little bit on future work, and then I'll wrap up and take questions. In some sense, this became the main kernel that we've been trying to extend at the University of Chicago in a bunch of different grad student projects, right? Now, the second that you've turned this query optimization into a prediction problem, right? We've taken this query optimization problem that was classically combinatorial planning, and we've turned this into a prediction problem. You can do all sorts of cool things. You can couple this with pre-computation. Now, what happens if I just don't want to figure out what's the next best join to make, but whether I should persist the result of that join in memory or not, so a future query can reuse it? Guess what? That's just a different reward function, and we can optimize that. So one of my students, Shi Liang, has been working on building a materialized view maintenance framework that is based on this query optimizer. And the cool part is, it just doesn't optimize a single query. It actually optimizes and adapts to a workload. So if you see the red line is what happens if I do per query optimization. The blue line, which is our predictive model, can actually significantly over time reduce the overall amount of compute that you're spending by intelligently persisting results that you predict are going to be useful in the future. Now, we also can think about other reward functions, right? We don't just necessarily need to optimize for performance. Sometimes we might have dirty data or uncertain data and might be interested in optimizing for accuracy instead. Suppose we have data that looks like this, right? This is actual data we collected from USAID, where we have ages that are listed in numbers and in terms of like English ages, right? And we have a bunch of these tables sitting in our industrial commercial data lake, and we need to merge all of that information together. Now execution order has implications on accuracy, not just performance. And if you're interested in optimizing for accuracy, you don't need to come up with a new heuristic. It's just a different reward function. And that's really cool. It's like, so we applied DQ. We're in the process of applying DQ to this thing. It's one of my students, Amy Zhang, is working on this. Just to sort of wrap up, again, what DeepRL gives us is, it gives us a new perspective on query optimization that allows us to decouple the notion of reward from the notion of search. And instead of coming up with a priori heuristics that are carefully tuned to the domain problem that we have, it allows us to decouple this and work with new database architectures, new database objectives, and new types of search spaces. Thank you.
Great talk, thank you. I find it very interesting about the RL framing of the problem.
Yeah.
I'm curious about your thoughts of how this RL approach can be extended along 2 dimensions. First is handling other types of operators like filter push down.
Yeah.
But in general, can we frame a general query plan graph instead of just a join graph? Second one is what happens when the query comes in and it references a new table you haven't seen before. Thank you.
Good. So to answer this question in 2 ways, I think it gets to the heart about what is part of this problem. It is fundamentally hard to featureize programs. Just because they are hierarchical and doing this kind of bag of words type analog that we're using right now is not going to work for these hierarchical structures. So we are in the process of looking at ideas like TRIL-STM, ideas from the NLP community. The open world problem is slightly harder. That's unclear how to solve when we see something that we just haven't seen before. At the least, we don't know how to do it. We might, in any real deployment, we're going to have safety checks to see if there's sufficient confidence and maybe fall back with permanent. I completely understand this is one extreme end of the spectrum. There is probably some middle ground that is commercially practical. But the first problem we are looking at using techniques from NLP like TRIL-STM is kind of on our radar of how we're going to approach it.
So thanks for the wonderful talk. So I'm also interested in applying deep RL in systems. So I saw you're using DQN in your work. I'm wondering, do you have any experience on when should we use value-based method, when should we use a policy gradient method?
Oh, this is an awesome question because this actually mattered in our application. So the reason that we use DQN is the data that we collect is actually not episodic in this problem. It's because that the nature of a join trajectory, the sequence of joins that you're taking, is every single sub-trajectory is in some sense its own query. And you can't just feed that into a policy gradient problem because that would mean that you don't have IID episodic rollout. And we found that DQN was much more robust to having non-episodic data than an on-policy method that would require these IID exploration things, right? So you would end up either burning data with not exploiting sub-query structure because they're all highly correlated if you use a policy gradient or a PPO or your favorite on-policy method. And DQN just turns out to be more robust. I would like to figure out the underlying mathematical reason for why there's no fundamental reason why we shouldn't be able to do this because there is some Markov structure in this problem that we should be able to exploit. We just couldn't figure out how to do it. But it's an awesome question. I think it's like, what I really like about this problem is that it's a nice, clean application, but it also gives us some idea about what the machine learning challenges are. Dealing with non-IID data, dealing with exploration patterns that look different than what we're used to, say, robotics or self-driving cars. This happens in these systems because we can actually set the state. This is a great question, and I think it really depends on your problem. And this non-IID nature of the data is really the reason we use the DQN. Great question.
I think there's time for 1 or 2 more questions. All right, well, let's thank the speaker.
So it's a great honor to have Jeff Dean as our keynote speaker. He totally doesn't need introduction, but I'm just going to say all of them. He's a senior fellow at Google. He's the head of Google AI, Google Brain lead and co-founder, and co-designer and implementer of software systems like TensorFlow, MapReduce, Spanner, Bigtable, and so many others.
Okay, thank you very much. So what I'm going to talk to you today about is first some research that we've done in applying machine learning to different kinds of computer systems. And then second, some ways in which we think this can be made more practical and easy for doing this in the future. So I want to point out that a lot of the work that I'm presenting is the work of many, many people at Google, so it's not purely my work. But as the previous speaker said, and throughout the day, we've actually heard examples of why this is an interesting direction. And the reason is that computer systems are really filled with all kinds of heuristics for query cost optimization, heuristics for how should I do instruction scheduling in a compiler, or which loop nest should I prefer given how big I think my caches are and so on. And these heuristics really have to work well in the general case. So they have to be written in such a way generally that they work well as you deploy software onto lots and lots of different kinds of configurations. They generally aren't able to adapt to how the system is really being used, except in fairly limited ways. And they often don't take into account like other additional context that could be used to make the decision, because it's sort of hard to know how to use that sort of information. And if you look across the spectrum of traditional computer systems, there's a really wide range of places you can imagine using machine learning, or better sort of online learned decision making rather than these heuristics. They often have the property that they have to be really lightweight for some of these kinds of decisions. But I think there's just tremendous opportunity to now rethink a lot of how we make decisions in computer systems. Everywhere from ASIC design, which we've heard some talks about today, all the way up to higher level software systems and compilers and OSs and job scheduling and distributed systems. So the key benefits are that we'll be able to adapt to the way the system is being used. And it's often hard to identify or hand code the right heuristics, because we don't necessarily know when we're writing the software how our users of a system are actually going to make use of it. You know, if we expect that, you know, database tables are going to be small, and suddenly some user pushes the boundaries and database tables are suddenly much bigger than we expected when we wrote heuristics, those heuristics are not really going to necessarily be right. And then the other benefit is online learning. We can actually have these systems adapt to this actual usage pattern. But the key challenges in this space are, how can we integrate machine learning into the guts of traditional computer systems? And in many cases, that really means, how do we make machine learning work well in really challenging performance environments? So if you're trying to make low-level decisions be learned, things like, you know, should I insert this block in my buffer cache, or, you know, which process should I schedule next? Those have fairly tight performance constraints. So you really need a system that allows you to have fairly lightweight usage of a model, and then relatively infrequent sort of heavier weight training of those models. And then there's a whole bunch of issues that I'm not going to go into too much, but if you start to have these things in the middle of your computer systems code, interpretability, understandability of these models can sometimes be important. If you're tasked as an operations person in a large distributed system, and all of a sudden your distributed system is made up of perhaps hundreds of little teeny machine learning models that are making decisions, you really might want to be able to understand what's going on under the covers. And at least with heuristic-based systems, you do have that ability to understand things a bit better, because you can sort of like grab the code and look at it. Safety and reliability, like you want to perhaps provide bounds of reasonable behaviors for these systems, and have the machine learning system select among reasonable sets of safe behaviors and not kind of go off the rails in various ways, and so on. I'm not going to talk too much about those, but these are sort of open issues as we start to do more and more of this in the computer systems space. Okay, so what I'm going to do first, the rest of the talk will be in two parts. First is a sampling of some work that is how we've applied ML to some systems problems that are not of the flavor of really fine-grained heuristics. And then the second part is a set of work that we're starting to do, where we actually are trying to build out a framework that allows us to integrate learning in a much finer grained way into the core computer systems. Okay, so one area that you can use machine learning is, how do you actually take something like a computational graph for a machine learning model and then be able to run it efficiently on a set of devices you have available. And this is essentially how do you get good model parallelism given some devices. And so if you imagine a large machine learning model, it may be that you want to run a single copy of that model across multiple devices and get good throughput using more than one device. And so in that case, you might decide to, for example, a human expert might decide to put different pieces of this model on different GPUs, and then have communication of the activations between the different GPU cards, because that allows you to essentially pipeline things and get good performance that way. But you can actually use reinforcement learning in this way to essentially make placement decisions for groups of nodes in a computational graph. And then after you've made placement decisions for all the nodes in the graph, you can then measure the execution time, and then use that as a feedback signal for the reinforcement learning algorithm. And then you can sort of repeat this and eventually get good performance. And this measured time gives you this clean, crisp RL reward signal that you care about. And with this, you can actually have the RL algorithm come up with fairly exotic placements that humans probably would not have come up with that are actually significantly better than existing human sort of human expert placements for these different kinds of models. And this is sort of the first work that we did in this space where we sort of pre-clustered pieces of the computational graph, because the computational graph tended to have tens of thousands of nodes, perhaps 70 or 80,000 nodes. And we didn't want to make individual decisions for each one of those. So to simplify it, we sort of pre-clustered it and then had the RL algorithm place those clusters of nodes. In follow-on work, we actually had the clustering be also learned. So we started with a raw graph, learned how to cluster it, and then learned how to place those clusters in an end-to-end manner. And we could then have the RL signal also feed back into the decisions of how the nodes got clustered. And with that, we're actually able to get significantly better performance. And this is work that appeared in ICLR earlier this year. Okay, so that's one example of using machine learning for a computer systems problem where you actually care about throughput of a model on a set of devices. And a really nice property it has is if you decide you want to use 6 GPU cards instead of 4, the system will just adapt to that. Whereas it's not necessarily obvious as a human expert how I would suddenly take advantage of 2 more GPU cards in placement of one of these models. It's an expensive slide. It's really important to optimize for power. Okay, so another bit of work that I haven't been involved in, but some of my colleagues have been doing, is how do you actually balance accuracy and inference time in neural architecture search. So our group published some early work on neural architecture search where we essentially try to find highly accurate models for a problem we care about. But often those models are fairly expensive because more accurate models tend to be more computationally intensive. And you often have either hard or somewhat soft constraints on the inference time for a model as you're going to deploy these systems in, say, self-driving cars or on mobile phones where you actually have some computational budget that you need to do. And so you want the most accurate thing that meets your other computational requirements. And the usual approach that you might do with this is you might fiddle with the model cost and computational expense and fiddle with measuring the accuracy until you get something that's reasonable, trying to balance these by hand, running lots and lots of experiments as a sort of human ML practitioner. But it turns out that you can essentially slightly change the reward function for neural architecture search into something that takes into account both the accuracy and the latency. So you essentially can train the model, collect the accuracy, actually run the model, say on mobile phones, collect the latency of that model, and then use that as inputs to a multi-objective reward function that blends those 2 signals together in a way that is appropriate. And for example, you might decide that you really want to meet an 80 millisecond target and then have the reward function drop off steeply, as you see on the left-hand side here, if you don't meet an 80 millisecond target. Or you might decide you want to weakly penalize things that are a little bit higher than 80 milliseconds, but then continue to fall off so that it will allow you to not be exactly 80 milliseconds, but better things are going to get better reward, or faster things will get better reward. And you can see that here. If we use the first cost function, each dot here is sort of a accuracy in the y-axis and an inference time on the x-axis. You can see that it really does explore only the region of 80 milliseconds or less models or a little bit above. Whereas if you use the softer reward function, the system is able to explore a little bit farther out and consider models that are maybe 100 milliseconds or 120 milliseconds, and can then find appropriately accurate models that have the right blend of accuracy and inference time. And this paper published had a bunch of different measurements, but if you hone in on just a few of them, you can see that NASNet there doesn't consider the inference time. It mostly is purely optimizing for accuracy. And these MNASNet papers or lines are actually optimizing for this combination of inference and inference time and accuracy. And you see that it actually gets to a significantly higher basically a little bit higher accuracy, but considerably faster in terms of inference time, which is what you want. Another area that has been interesting is how can we use machine learning models to effectively replace conventional index structures in things like database systems. So if you look at data structures, they're all designed to work for worst case data distributions. They don't really take advantage of the distribution of data that you're actually processing in the system. And so if we have data structures that can then learn from the distribution of data that we're actually using and processing, we might be able to do better than distribution oblivious kind of data structures. And so if you think about a B-tree really is a model that allows you to take in a key and then give you an approximate position of where that key must be in some sorted data structure, be it a sorted disk table or maybe an in-memory data structure. And so you know that if you get to this bottom part of the B-tree, that key will definitely be somewhere within that page of data. So if you squinted that just right, that looks a bit like a model where you can actually have something instead of a B-tree that does the same function. It gives you take in a key, and then you produce an approximate position whereby you know that in some range near that position, the key is definitely either going to be there or it won't be found at all in the data. And by doing that, you can actually get things that are significantly better in various ways than B-trees. And so you can think of this as trying to predict the position in the cumulative distribution function of where that key must be in the sorted distribution. And so, for example, if you compare this to a B-tree, you can actually get something that is 60% faster than a B-tree at 1/20th the space. And it has the other nice property that you can make a variety of different trade-offs. If you want something that's, say, 17% faster, it can be 1/100th the space. And that really does change the fundamental way you might think about indexing things in a database system. And this also works for learning hash functions. So instead of a traditional hand-coded hash function that is not aware of the distribution of data, you can create a model of the data distribution that you're likely to be hashing, and then make better utilization of the buckets in your hash table because the system can take advantage of that distribution. And similarly with Bloom filters, you effectively can learn a Bloom filter model that allows you to get effectively more compact Bloom filters than traditional Bloom filters for the same false positive. So that's some computers, sort of machine learning applied to what I think of as traditional computer systems problems. But I think one question we want to ask is how can we actually embed learning into existing computer systems in an easier way? The other things I've described so far are really like whole computer systems almost that are going to do one of these computer system tasks, rather than sort of very lightweight things you might imagine putting in the guts of an operating system or something. So we want systems that can do these kinds of optimizations automatically, but we already have lots and lots of computer systems code, right? Like it's not like we're going to throw away our operating system code base and start it from scratch. So I think what we need is really simple APIs that enable us to, for the few places where we think this is going to make a big difference, embed this kind of learning in the middle of existing computer systems code with fairly minimal changes. So we're actually building a system and an API for this called Smart Choices that we think will allow this. We've got some early experience internally. We haven't yet published any papers on this, but we think it's pretty exciting. So I'm going to sort of sketch out how we imagine this might work. And I'm going to do this in the context of an example, a motivating example from Bigtable, which is a large-scale distributed storage system. So the way Bigtable works is you have lots and lots of client jobs running on different machines. You have these blue tablet servers that are responsible for maintaining the state of a bunch of tables in the system. And then those things are persistently stored in a set of sort of distributed file system servers that are shown in green. And so if we zoom in on what happens for a particular client request, a client may say, hey, I would like to read something from the table, and it will communicate with one of these tablet servers, and then that will perhaps read some data from one of these trunk servers. And so if we zoom in a bit further, the read operation says, hey, I'd like to read from this table, this key, and these columns from that table. And that request is made by a particular client name from a particular job with a particular task ID. And then inside the big table tablet server, there's code that looks like, if that will read this data from the distributed storage system, and then it has an in-memory block cache because there tends to be locality in these kinds of things. And so there's code that looks like, if I should insert this block into my in-memory cache, then I'm going to go ahead and insert it. And that code will look like, some heuristic that is written that looks at the properties of the block and maybe some other things and decides whether or not to insert it. So one thing we do know about these requests is we know the job name. And at Google, we actually have a convention of MapReduce jobs start with MR-. And we run millions of MapReduce jobs every day. And MapReduce jobs have this particular property that they're generally doing a sequential pass over a bunch of data. And you actually never want to insert it in the memory cache because there's almost no locality, right? You're just going to sequentially pass over the data, not look at it again until you run the next job an hour later or something. So you can imagine writing a heuristic that says if the job name starts with MR-, then don't insert it in the cache. But that would be crazy to handwrite in like the middle of your core computer systems code. You would never write that. But that is probably what you want, right? And it's through learning that we're going to be able to get behaviors like this that adapt to particular additional information that is available when you're making these read operations that you would never actually really write a heuristic in a hand-coded way to take advantage of. So the way we're going to do this is we're going to say if learned should insert with a bunch of additional contextual arguments like the name of the job, maybe the name of the user, the name of the table, and then we're going to return inference of some model. And that is how we're going to be able to take advantage of this additional information that is available that is not sort of directly related to the decision of which of the block, but is also available at the point at which we're making these decisions. And so the sketch of the API, there's sort of four main concepts. One is called a choice, which is basically application code will call this code, call a choice to make a decision, and it can provide, what are the acceptable values of the choice I'm trying to make. There's feedback, where the application code can report some reward feedback later, perhaps, when it has some metrics about how well something worked. There's an activity, which ties together choices and then later on feedback. And then there's context, which has information that might be useful for making a choice inside of an activity. So it might be additional things like the job name or the table name or other kinds of things that you think should perhaps feed into this. And there's a couple of, a bunch of things you want to consider. So one is these actual inference of these models must be quite lightweight, right? Like if I'm going to actually decide to insert this block into block cache, that can't take, a second of computation. That involves like a, 100 microsecond kind of thing. It needs to support lots of different kinds of models and different learning algorithms, different implementations to support different deployment settings, which I'll go through in a minute, and needs to be robust to failures, for example. So if you look at sort of a variety of different scenarios, the simplest scenario might be where you have a single process and you're doing all of this choice-making, feedback reporting, and learning of models in the context of a single process. And for that, you can imagine that both the choices and the feedback emit entries into an in-memory log buffer that you can then consolidate by these activity IDs and make a decision and then basically do periodic training on this sequence of choices and then feedback. And then periodically you can create a model that's based on all this and update the serving model. Now, in a distributed setting, it may be that the choices you make are on one machine and then some of the feedback you get is on a completely different machine. And so in that case, the flow that you want is roughly the same, but the system is more complicated because now all of a sudden you're logging things probably under a distributed file system. The collection of feedback and other kinds of things is coming from all over the place. It's getting centralized in a on-disk log buffer. There's a periodic training system still, but it's reading out of this on-disk log buffer. And then when you update the serving model, that becomes perhaps more complicated because now you may have many clients that all want a view of this serving model perhaps so they can make similar decisions as you push a new model out. But conceptually, it's the same. It's just sort of more mechanism. And there's lots of variations. So maybe logging every decision you make is too expensive. So you can imagine sampling 1 in every 100 or 1 in every 1,000. It might be that you want a very cheap model. So distillation is a common way where you could take a more expensive model and then produce a cheaper model that approximates the behavior of that more expensive model. We think that could be quite useful for some of these scenarios where you really need like 100 microsecond variation of the model, and you can't afford much more compute than that. You can imagine freezing things. If you don't want to do continuous online learning, but you have some representative usage of your application, and then you maybe want to ship a version of it in a mobile phone where you don't want this complexity, you can imagine freezing things based on this representative behavior and then using the learned behavior, but without updating its behavior over time. And there you just have a program binary plus a bunch of these embedded little machine learning models in the middle of that program binary somewhere. So our next choice is we're refining this API, and the initial implementation is working with about 10 early uses that we've identified across Google. Many of these uses are computer system style problems, but it's also useful for other kinds of things like, what treatment in a UI do I want? Is this UI better than this UI? Using some then measured reward from how users actually interact with the system. So it's not just computer systems code that we imagine using this. We think there's a lot of room for these kinds of really easily integrated machine learning models in the core of a traditionally written hand-coded computer system. With that, I think machine learning for computer systems is really a relatively new and exciting area for doing a lot of much better behaving systems than what we have today. Learning in the core of computer systems is really going to make them better and more adaptive. But there's a lot of complexity as we start to add more and more of these little learned choices in the middle of large-scale computer systems. I don't think we fully understand the implications of that or how to really make them interpretable and safe and so on. But I think the potential is there, and we should really push on this research direction. So thank you for that. And now I guess I'll take questions when we have a panel. Yeah.
If you raise your hand, I'll bring the mic over.
Are you planning to make smart choices available outside of Google?
Yeah, we will likely publish a paper and then likely open source the key parts. But we don't have a timeline for that. We don't.
So as you start delving further down into the stack, and this is in the context of smart choices, obviously you can expose pretty big risk surface. So if you change a really core system that's used by lots of other systems, a small change here could have massive downstream implications. How do you test such a system and ensure that this new model that you're training isn't going to break something?
Yeah, I think this is obviously one of the open areas of how do you actually do a much better job of testing if the system can be adapting continuously. I think this is actually a more general problem than just the smart choices kind of work. I think, over 30 or 40 years, we've actually built up a pretty good understanding of how to write highly reliable, safety-critical software in a hand-coded style. And I think as we've transitioned to start to do more machine learning, we don't necessarily have the equivalent toolbox for learned systems that we have for hand-coded safety-critical systems like avionics systems and things like that. And I think really that's a place where the community should be doing more work and is sort of an active area of research, but is not sort of fully solved by any means. I think we're going to essentially come up with engineered solutions that are the equivalent of unit testing and integration testing for these kind of systems. That is kind of a little underspecified at the moment, but I think that's the way we'll make progress.
The chunk server and the .NET server that I talked about, I'm assuming you're running really old CPUs and traditional Intel x86 processors. So, and like you're talking about doing the inference and the training all on those boxes, do you think we will be able to do, and they're also real-time systems, so have high performance constraints, and we will do a good training and inference of those boxes in the 100 microseconds?
Right. I don't think the training has to necessarily be done in super fast thing. That you can have a offload to a machine learning accelerator like a GPU or a TPU or something. I think the inference does have to be fast. And I would have two answers to that. First, I think you can train fairly lightweight models. So the B-tree learned index-related code work actually showed that we can have very lightweight models that run on CPUs and are more efficient than even traditional B-tree operations because they're effectively like a few multiplies and adds, and you traverse kind of a much larger model, but do very few operations in order to do that. So that's one aspect of the solution. The other is I think future processors will likely have more onboard capability for doing better sort of machine learning oriented computations like sort of lightweight linear algebra kind of computations, and that will also help.
So we expect to ship the logs to a different GPU or something for the training and do the inference on those boxes.
Yeah.
We have time for just one more question, which is everybody's over here, and then we'll set up the panel discussion.
When you select to apply ML for system, what are the criteria? Maybe some systems like near the optimal, like criteria for that.
Right. I think we don't have kind of a. One thing you can do is try to, if it's a problem that's amenable to like an Oracle-based evaluation method with a tracing-based simulator or something, then you can see what the gap is of the current system and what an Oracle could do, right? That gives you an upper bound on what you can possibly do with learning. I think the other thing that to think about, sort of not quite so formally, is there a lot of contextual information available here that might help make better decisions than the heuristics are currently taking advantage of, or that maybe the heuristics don't really are able to comprehend the kind of way in which the system is being used. I think that's the way you'll figure out what are the highest impact places to try this first. But as we get more experience with this, I think we'll develop better kind of ways of squinting at a problem and saying, yeah, that looks like a really good one, and that one probably not. Okay. All right.
Okay. Thanks so much, Chuck. Stick around. We're going to have a panel discussion with Jeff, Parker Sung Han, and Ion Stoika.